Hello, I'm myself Dr. Vineet Nair from Department of Physics, CMD PG College, Bilaspur. This is a visual presentation of the lecture which was already submitted in our Google Classroom. Lecture is lecture number 5 of the series of lectures which we have posted in the Google Classroom. This lecture belongs to the semester 2 students of MSc Physics. It is about the Unit 1 Electrodynamics, and the title of the lecture is Electromagnetic Waves in Vacuum. It is in fact the part 1 of the lecture 5 which was submitted in the Google Classroom. So students, coming forward to the lecture, we all know that when it comes to electromagnetic field, it is a fact that we don't see that field. The only way to describe that electromagnetic field is in the terms of the mathematics of Maxwell equation. The fields we all know are oscillations in three dimensions. The field is oscillating, and it is just like the oscillation of the displacement in a mechanical wave. We also know that there are both electric field and magnetic field. The mathematical description of the electromagnetic field is done by the use of Maxwell equation. Maxwell equations describe all the phenomena ranging from frequencies as low as zero to very high frequencies as optical frequencies. The four Maxwell equations are in fact in terms of the displacement flux density, divergence of D equal to rho, divergence of B equal to 0, and the two curl equations. One of the Faraday's law, which shows that a time varying magnetic flux gives rise to an electric field, and the modified Ampere's law, which shows that there are two components of current density which give rise to magnetic field. One is the free conduction current density and the other is the displacement current density. Now we restrict, as the title of our lecture is the electromagnetic waves in vacuum. Basically, when we start saying that we are studying the electromagnetic waves in vacuum, we have to basically identify the electric field vector and the magnetic field vector in such an electromagnetic wave. What is the orientation of these waves, of these fields, whether they are collinear or they are perpendicular to each other, what is the direction of the electromagnetic wave. So there are in fact three vectors: the E field, the magnetic field, and the propagation vector. Now consider a situation in which we uh, consider a region of space which is free of any type of charge density and current density. So both the volume charge density rho and the current density J are zero. However, a question arises whether the Maxwell equations will be valid in such a region, which is devoid of free charges and current density. The answer will be yes, the Maxwell equations will still be valid here. And we should understand that except this region in which rho and J are zero, at very far away distances, extending from minus infinity to plus infinity, rho and J are both non-zero. So the four Maxwell equations become divergence of D equal to 0, divergence of B equal to 0, curl of E equal to minus del V by del T, and the modified Ampere's law remains the same. Note that it is important to understand that E and B are themselves non-zero in this region of interest, where rho and J are both 0. This is because the E fields and B fields are self-sustaining fields, means they both support each other. The operational definition of what electric field and magnetic field, it comes from the Lorentz force. We all know it. This is a point to remember. So if there is charge in vacuum and it experiences a force, then there is if it experiences force, then we can certainly say that electric field is present there. On the other hand, if it experiences a force when it is moving, then there will be a magnetic field also. So this tells us that although we cannot see those fields, there is an electromagnetic field. Uh, to see how the symmetry introduced by Maxwell accounts for the existence of combined electric field and magnetic fields that propagate through space. Imagine a time-varying magnetic field B0, which is a function of time produced by the highly high-frequency alternating current, which is shown in the figure just below. We represent B0 in the diagram by one of its field lines. We are not showing the entire schematic of the field lines. From the Faraday's law, we know that the changing magnetic field through a surface induces a time-varying electric field at the boundary of that surface. The displacement current source for the electric field, like the Faraday's law for the magnetic field, produces only closed loops of field lines because of the mathematical symmetry involved. A field line representation of E0 is shown. In turn, the changing electric field creates a magnetic field B1T. So the original magnetic field was B0T, and now the changing electric field produces a new magnetic field B1T according to the Ampere's law. This changing magnetic field in turn again, this changing electric field produces the magnetic field and so on. So we have a self-sustaining mechanism in which a changing E or B gives rise to the other magnetic fields. We then have a self-continuing process that leads to the creation of an electromagnetic wave or time-varying electric fields and magnetic fields in a region very far away from O. This process is visualized as the propagation of electromagnetic wave. So in this diagram, the alternating current is flowing here. There is a single magnetic field line B0, and now B0 is a function of time, so it produces an electric field around the closed loop. And this electric field is again a function of time, so it produces a magnetic field. And so this process goes on, and the wave propagates in this direction. Now, the first part is of this lecture should be having visualized that there is an electromagnetic wave associated with the oscillations of electric field and magnetic field. We should be able to establish the wave equation. So what Maxwell equations we have studied actually satisfy the wave equation. Now the divergence of E is equal to rho upon epsilon 0, or divergence of epsilon 0 into E is rho. Divergence of B can be again written as mu 0 into H. So where epsilon 0 and mu 0 are the electrical permittivity of free space, and mu 0 is the magnetic permeability of free space. The other curl equations are curl of E is equal to minus del B by del T, or minus mu 0 into del H upon del T. The modified Ampere's law is curl of H equal to J plus del D by del T, or J plus epsilon 0 into del E by del T. So in these equations, you can see that the electric field and magnetic field are both coupled. And this coupling is in fact responsible for the propagation of electromagnetic waves. Coming to our problem, in which we have assumed a certain region of space in which there is no charge density and current density. So we put rho and J equal to 0. And now going over to the curl equations, we take the curl of the Faraday's law. So curl of E gives minus curl of del upon del T of mu 0 H. Here we can, this is space derivative operator and this is the partial time derivative operator. You can interchange the two operators. So we have written minus del upon del T of mu 0 into curl of H. And curl of H is J is in 0. Since J is 0, so curl of H is del upon epsilon 0 into del E by del T. So we get minus mu 0 into epsilon 0 del square E upon del T2. So double time derivative. So curl of E is equal to minus mu 0 epsilon 0 del square E upon del T square. Momentarily, you can just see that mu 0 into epsilon 0 is a very special quantity. In fact, 1 upon mu 0 under root of mu 0 epsilon 0 is the velocity of light in vacuum, which is nearly 3 into 10 to the power 8 meters per second. Going over to uh, this uh, step written in the left hand side, you can solve it by using the vector identity. Curl of a vector is gradient of divergence of a vector minus del square of the vector. So you can write gradient of divergence of E minus del square E equal to this. And we all know that for the problem concerned, which is a region of free space, no R, no rho, and no J. So you can put divergence of E equal to 0, and thus we come to the uncoupled wave equation for E, which is del square E equal to 1 upon C square del 2 E upon del T square. So this gives the equation of a wave traveling at a speed c in free space. This is in fact equal to three scalar equations, and you can write these scalar equations as follows. Definitely waves must satisfy this equation, which is again the divergence of E equal to 0. Similarly, we can obtain a wave equation for the H field by using the modified Ampere's law, taking its curl, and in here, if you take the curl, then curl of H is equal to curl of J again is 0, so curl of epsilon 0 del U by del T, and curl of E you can substitute from the Maxwell equation, and we can get the similar wave equation for the H vector. So both the equations written in the compact manner shows that these are three-dimensional wave equations for electric field and magnetic field, where C is the velocity of the speed of light. This means that even in vacuum there are excitations. The excitations are of the form of the electric field and the magnetic field, which propagate, and we have the wave phenomenon. So the important thing to remember is whatever be the solution of the system of the Maxwell equation, and whatever be the solution of the problem, it must satisfy the Maxwell equation. In general, any basic wave equation is written as del square psi equal to 1 upon c square del 2 psi upon del t square. In fact, there is not a it resembles a basic equation, but we have substituted the velocity as the speed of light, where psi represents in the E field or the B field or any of the six components of E and B. This equation determines the properties of most wave phenomena, not only light waves. This is second order homogeneous differential equation. A very important thing to remember about such equation is that this general solution has two unknown constants, which cannot be determined without some additional information about the problem, such as the boundary condition. And the other important aspect of the solution is that they may be the ordinary oscillatory solutions which involve sine and cosine functions. Now, here we have given a simple one-dimensional form of the equation for scalar function f. So psi has become a scalar function f. The solution to this one-dimensional equation is represented as, it should be definitely of the form of f. It is one-dimensional function, so f is a function of x plus minus vt, where v is the velocity of the wave. X minus vt represents a wave propagating in the right direction, and x plus vt represents a wave which is propagating in the negative x direction. Any function with dependence on coordinates x and t of the form x plus minus vt will definitely satisfy this equation. And you can definitely prove it. I have proved here. You can go through this. Another useful form for the equation is to involve the cosine and the sine wave solution. Even more useful form for the solution is representing waves using complex numbers. So that methodology we have adopted here, and we represent an electric field as E as a function of x and t equal to E0 exponential I kx into x minus I omega t, where omega is the angular frequency in radians and k is the wave vector and lambda is the wavelength. The general plane wave solution of the above equation should be of the form psi equal to psi 0, where psi 0 is again a constant vector and exponential I k dot r. Here k becomes the propagation vector. Here you have substituted just the x component of the k vector, where psi represents the components of E and B, and kx, ky, kz are the components of the propagation constant, and psi 0 is the constant amplitude vector. In terms of the electric field components and the amplitudes of x, y, z components of the field, you can write Ex equal to, this is the amplitude of the x component of the electric field, Ex0 exponential I kx into x plus ky into y plus kz into z minus omega t, similarly for Ey and similarly for Ez. You can write a similar components for Bx, By and Bz. Bringing the first Maxwell equation, which is divergence of E equal to 0, which means that del Ex upon del x you calculate it, del Ey by del y you, and del Ez by del z you again calculate it, and you combine it, you find that divergence of E comes out to be I k dot E. And since divergence of E is 0, therefore I k dot E is 0. And this means that the propagation vector k is perpendicular to E. Same things can be repeated for the divergence of B using this equation, which again gives that k is perpendicular to B. So k is perpendicular to E and k is also perpendicular to B. This means that E and B vectors are both perpendicular to the propagation vector k. However, these relations don't ensure the orientation of E and B fields. Means how E is oriented with respect to B, that idea you have to still explore. To check this, we consider the third Maxwell equation, which is the curl of E equal to minus del B by del T. हाँ, अरे यार 2 मिनट क्या यार